Sometime 4 p.m. NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again. NASA engineers have re-established communication with the Voyager 1 spacecraft, Earth's most distant emissary, after months of troubleshooting a glitch that had rendered the probe's transmissions unreadable. What shocking discovery has NASA's Voyager probes made after 45 years in orbit? Despite having little memory and sluggish data rates, these 1977 launch spacecraft have been at the vanguard of interstellar research for a considerable amount of time. But Voyager 1 has recently returned data that has scientists puzzled and worried. Information about the control system is inconsistent with how it is now operating, suggesting an impossibility. Come along with us as we explore the universe to solve this riddle. On September 5, 1977, Voyager 1 was launched into orbit from Cape Canaveral, Florida, using a Titan IIIe Centaur rocket. An incredible trip had begun. With this, on August 20, 1977, 13 days prior, Voyager 2 began a corresponding space mission, starting a parallel trip. Their primary objective at first was to investigate the moons of the gas giants Jupiter and Saturn in our solar system. These brave adventurers far exceeded their original objectives by embarking on a trip that would lead them to the furthest reaches of our cosmic neighborhood. Voyagers 1 and 2 have broken many records during their historic mission, having outlasted every previous spacecraft in history. They have flown farther from Earth than any other human-made object, into interstellar space. These are the first objects created by humans to explore portions of the galaxy that are yet unknown to science. Beyond the influence of the sun, scientists have gathered an immense amount of priceless data. These groundbreaking interstellar probes are located more than 12 billion kilometers from Earth, and their discoveries never cease to astound physicists. We'll talk more about one amazing and unanticipated discovery later on, something scientists could never have imagined. The twin probes of Voyager have accomplished amazing things throughout the years. Over 40 years ago, they made the astonishing discovery that there were moons on Jupiter and Saturn, shocking scientists and upending their preconceived assumptions about these far-off planets. These moons turned out to be throbbing with geological activity, defying earlier theories that they would be dead and cratered like our own moon. Particularly during its voyage, Voyager 2 accomplished a number of noteworthy milestones. As the first spacecraft to sail past Uranus, it made history in 1986. It was the sole spacecraft to fly past Neptune, having done so 3 years later. From Neptune's ferocious winds and icy volcanoes on Triton to the hitherto undiscovered moons of Uranus, this amazing voyage provided a plethora of knowledge about these far-off ice giants. NASA has implemented multiple procedures aimed at extending the spacecraft's operating lifespan. By turning off heaters and non-essential parts to save energy, the spacecraft will continue to operate far beyond the next 10 years, since the Voyager mission is planned to conclude in 2030. This meticulous management guarantees that they will be able to continue returning data as long as possible. For the scientists and engineers who have been involved in this amazing journey from the beginning, the Voyager mission's end is a moment of mixed emotions. A mission far more successful than anyone could have imagined has resulted from their commitment and tenacity. Many scientific advances and significant new understandings of our solar system and beyond have resulted from the data that the Voyagers brought back. Future generations of scientists and space enthusiasts have also been inspired by them beyond our wildest expectations. Before their launch, the Voyagers have experienced and captured the wonders of our solar system. These missions have revolutionized our knowledge of these celestial worlds, revealing secrets like the frozen shell of Europa, the towering volcanic plumes on Io, one of Jupiter's moons, and the amazing discovery of Jupiter's thin rings. Previously believed to be lifeless and desolate, the amazing pictures and data they returned showed lively and active worlds. New questions emerged as Voyager 2 traveled farther and encountered Neptune and Uranus, highlighting the richness and complexity of our solar system's outer planets. The finding of 10 hitherto undiscovered moons around Uranus and the harsh weather on Neptune, where winds might reach 1,000 miles per hour with surface temperatures down to -391 degrees Fahrenheit (-235 degrees Celsius), were startling. Triton, the biggest moon of Neptune, was discovered to be among the solar system's coldest locations. Other surprising discoveries included the ice volcanoes of Triton, which released frozen particles and nitrogen gas as Voyager 2 carried on its extensive exploration of the outer planets. Voyager 1's trajectory brought it dangerously close to Saturn's moon Titan, exposing its hazy orange atmosphere and intricate chemistry. Many new concerns regarding the nature of these far-off worlds were raised by each encounter, which yielded a plethora of data that challenged preconceived notions. Ordinary spacecraft were not what Voyager 1 and Voyager 2 were. Their precise design called for them to be stable platforms rotating at a rate that is over 15 times slower than a clock's hour hand. Because of its design, there was less visual blur as the spacecraft was speeding through space and taking pictures and data. Even before they encountered the outer planets, their astounding imaging skills started to amaze scientists and the general public. While still several months away from Jupiter, the spacecraft began to transmit photographs of the planet. The gas giant's whirling clouds and recognizable Great Red Spot were seen in these early photos, which thrilled viewers at NASA's Jet Propulsion Laboratory. But the real catalyst for the Voyager's groundbreaking observations was the finding of active volcanoes on Jupiter's moon Io. It was discovered that Io, a moon that is marginally bigger than Earth, is the solar system's most volcanically active body. Our knowledge of these far-off planets has changed as a result of the Voyager research of their moons and outer planets. The astounding discovery that Europa, the moon of Jupiter, may have an ocean beneath its frozen surface sparked curiosity about the possibility of extraterrestrial life. Similar to this, the finding of geysers flowing from Enceladus, the moon of Saturn, indicated the possibility of liquid water beneath the surface of the planet. These results have motivated follow-up missions to learn more about these fascinating moons and have significant implications for the hunt for extraterrestrial life. The experiences that Voyager 2 had with Neptune and Uranus were equally revolutionary. During the probe's approach to Uranus, it was discovered that the featureless blue-green planet had many moons, including the fascinatingly active Miranda, and a complicated magnetic field. Humanity received its first detailed photographs of Neptune in 1989 when Voyager 2 passed close to the planet, revealing its vibrant atmosphere, deep blue color, and great dark spot. In addition, the spacecraft confirmed that there are weak rings surrounding the planet and found 6 additional moons. The Voyager's equipment continued to send back important scientific data as they traveled farther into space, providing crucial data regarding the heliosphere. The bubble-shaped area of space dominated by the Sun's magnetic field and solar wind was supplied by the probe. The Voyagers were able to investigate the interstellar medium, the sparse environment between the stars, after passing through the heliopause, which marks the edge of the heliosphere. One of the most astonishing recent findings from the Voyager probes was the unexpected rise in cosmic rays found in interstellar space. This discovery has caused scientists to reconsider their theories about the interstellar medium and the environment beyond our solar system. The information gathered by the Voyagers on magnetic fields, plasma waves, and cosmic rays is still very helpful in understanding the composition of interstellar space and the mechanisms forming our galaxy. The longevity and success of the Voyager missions are a testament to the creativity and dedication of the scientists, engineers, and technicians who designed, built, and operated the spacecraft. The Voyagers have persevered in operating despite the extreme conditions and great distances they have traveled, returning data that has revolutionized our knowledge of the solar system and beyond. The missions have also brought attention to how critical robotic exploration is to advancing our understanding of the cosmos. NASA has put policies in place to preserve the Voyagers' remaining energy and prolong their missions as long as feasible. As they get closer to the conclusion of their operational lives, the spacecraft are anticipated to survive until at least 2030 if they carefully manage their energy supplies and shut off non-essential systems. Our knowledge of the interstellar medium and the outermost regions of the solar system will be considerably enhanced by the data they return during this period. Beyond their contributions to science, the Voyager missions leave behind a lasting legacy. Each spaceship is equipped with the recognizable golden records, which are audio and visual records that showcase the variety of life and civilization on Earth. These documents are a message to any future extraterrestrial civilizations that could come across the spacecraft. The Golden Record's presence reflects humanity's interest in and desire to establish connections with the larger cosmos. The Voyager spacecraft's breathtaking images confirmed the odd signals picked up from Io. These photos showed a dynamic terrain characterized by towering volcanic plumes and the discharge of volcanic debris. Pele, a well-known volcano on Io, is one of its most spectacular characteristics. Its eruptions have reached heights 30 times higher than those of Mount Everest, erupting across an area about the size of France. More than 33,000 images of Jupiter and its moons were taken by the Voyager spacecraft, demonstrating the grandeur of the planet and the remarkable diversity of moonscapes in the Jovian system. The twin Voyagers have continued to make groundbreaking discoveries ever since they were launched. The discovery that Jupiter had rings was among the most unexpected. These rings, however faint, increased the mystery surrounding the gas giant. In addition, earlier theories concerning these far-off celestial entities were called into question when Voyager 2 discovered that Europa, one of Jupiter's 53 named moons, had an icy crust more than 60 meters thick. This discovery opened up new directions for planetary science research by enticing scientists to explore the possibility of ice moons being habitable. The Voyagers got a vital gravity boost following their mission at Jupiter, which gave them one last push toward Saturn. They would never have been able to break free from the gravitational pull of the Sun and travel farther into space without this essential push. Voyagers 1 and 2 split up soon after, each traveling to uncharted territory. Voyager 1's trajectory brought it very near Titan, the moon of Saturn, which is enveloped in a thick orange atmosphere. Scientists' curiosity over Titan's mysteries led to more research into its intricate composition. After that, Voyager 1 moved north, leaving the planet system and starting its ascent outside of our solar system. On the other side, Voyager 2 set off on an extraordinary journey that brought it to the solar system's outermost planets. It made a landmark flyby of Uranus in 1986, finding 10 moons that were previously undiscovered and thus expanding the number of known satellites around the planet. Voyager 2 arrived at Neptune 3 years later, exposing the amazing features of this far-off ice giant. Voyager 2 reported wind speeds of up to 1,000 miles per hour during its approach to Neptune, the fastest winds yet measured on a solar system planet. Upon approaching Neptune's methane-laden azure atmosphere at a distance of 2,980 miles, the spacecraft offered unparalleled perspectives into this distant planet. It was discovered that Triton, the biggest moon of Neptune, is among the solar system's coldest locations, with surface temperatures falling as low as -391 degrees Fahrenheit. Triton also displayed unusual geological features, such as ice volcanoes that erupted up to 5 kilometers into its thin atmosphere, spitting frozen particles and nitrogen gas. Our knowledge of the variety and complexity of celestial bodies in our solar system, even in its furthest reaches, has increased as a result of these findings. In addition to expanding our understanding of the outer planets and their moons, Voyager 1 and Voyager 2 have contributed priceless data during their interstellar travels. The culmination of the Voyager study of the heliosphere, a huge bubble-shaped area of space where the solar wind is dominant, was the crossing of the heliopause, the point at which interstellar space begins and the solar wind's effect diminishes. Voyager 1 and Voyager 2 became the first artificially created objects to enter interstellar space when they accomplished this feat in 2012 and 2018 respectively. This transition advanced our knowledge of the border between our solar system and the rest of the galaxy by giving scientists a plethora of information on the characteristics of magnetic fields and interstellar plasma. It was discovered that Triton, the biggest moon of Neptune, is among the solar system's coldest locations, with surface temperatures falling as low as -391 degrees Fahrenheit. Triton also had peculiarities such as ice volcanoes that shot icy particles and nitrogen gas 5 miles into its thin atmosphere. Our knowledge of the variety and complexity of celestial bodies in our solar system, even in its most distant areas, has increased as a result of these findings. Astronomer Carl Sagan was one person who was instrumental in the missions going above and beyond their original objectives. As an imaging team member of the Voyager mission, he strongly supported taking one more round of pictures before the cameras on board both spacecraft were shut down, a farewell gift to humanity. Sagan's perseverance was rewarded. Voyager 1 aimed its camera back toward the inner solar system on Valentine's Day 1990 and took a set of 60 pictures. The most well-known of them, dubbed the pale blue dot, is an enduring representation of our position in the universe. Captured at a staggering 3.8 billion miles away, this is the farthest photograph of Earth yet documented. In the expanse of space, Earth appears as a small, pale blue speck that is hardly noticeable, a story of incredible sturdiness and longevity. The Voyager mission reads like a comic book about space-age superheroes. They have been sending us useful data from the farthest regions of our cosmic neighborhood for 40 years now. Let's now discuss their antiquated 8-track cassette technology. Yes, you read that correctly. The Voyager probes still utilize the 8-track records that were so popular in the 1970s. The fact that these reliable cassettes have endured over time is evidence of the mission's creators' brilliance. You might question, but why 8-track tapes? The concept of digital storage as we know it now was very new during those early space exploration days. They therefore required a dependable and long-lasting data storage solution, and the 8-track tapes worked well for it. They resemble the cosmic age's unbreakable workhorses. Even more astounding is the fact that the information on these cassettes contains priceless scientific data about the outer planets, moons, and interstellar space rather than simply ordinary music. These cassettes are the key to unlocking some of the universe's greatest mysteries. When considering durability, keep in mind that the Voyager spacecraft are subjected to high temperatures, space vacuum and cosmic radiation. Still, these elderly adventurers continue to go. It's similar to sending your grandparents on an Arctic hike, where they not only make it through but flourish. The experiences that Voyager 2 had with Neptune and Uranus were equally revolutionary during the probe's approach to Uranus. It was discovered that the featureless blue-green planet had many moons, including the fascinatingly active Miranda, and a complicated magnetic field. Humanity received its first detailed photographs of Neptune in 1989 when Voyager 2 passed close to the planet, revealing its vibrant atmosphere, deep blue color, and great dark spot. In addition, the spacecraft confirmed that there are weak rings surrounding the planet and found 6 additional moons. The Voyager's equipment continued to send back important scientific data as they traveled farther into space. Crucial data regarding the heliosphere, the bubble-shaped area of space dominated by the Sun's magnetic field and solar wind, was supplied by the probe. The Voyagers were able to investigate the interstellar medium, the sparse environment between the stars, after passing through the heliopause, which marks the edge of the heliosphere. The unexpected rise in cosmic rays found in interstellar space is one of the most astonishing recent findings from the Voyager probes. This discovery has caused scientists to reconsider their theories about the interstellar medium and the environment beyond our solar system. The information gathered by the Voyagers on magnetic fields, plasma waves, and cosmic rays is still very helpful in understanding the composition of interstellar space and the mechanisms forming our galaxy. NASA has put policies in place to preserve the Voyagers' remaining energy and prolong their missions as long as feasible. As they get closer to the conclusion of their operational lives, the spacecraft are anticipated to survive until at least 2030 if they carefully manage their energy supplies and shut off non-essential systems. Our knowledge of the interstellar medium and the outermost regions of the solar system will be considerably enhanced by the data they return during this period. The inventiveness and commitment of the scientists, engineers, and technicians who created, constructed, and managed the spacecraft are demonstrated by the Voyager mission's endurance and success. The Voyagers have persevered in operating despite the extreme conditions and great distances they have traveled, returning data that has revolutionized our knowledge of the solar system and beyond. The missions have also brought attention to how critical robotic exploration is to advancing our understanding of the cosmos. Understanding gravity assist techniques proved to be a crucial component of the Voyager mission's successful implementation of multiple important concepts, making them legendary interstellar voyages. Imagine Voyagers 1 and 2 setting out on their audacious mission to investigate the furthest regions of our solar system. They required more power than their propulsion systems could give to reach these far-off locations and collect priceless data. This is when gravity helped out, kind of like a cosmic dance. These spacecraft used the powerful gravitational attraction of some of the heavyweight planets in our solar system to propel themselves forward rather than depending just on their engines. By using this cunning move, they were able to save valuable fuel and increase their speed, which helped them reach more stops on their grand tour. A gravitational slingshot, or gravity assist, is a technique where a portion of a planet's velocity is transferred to the spaceship as it passes. Imagine Voyager 1 traveling toward Jupiter, a gigantic gas giant with a gravitational pull of its own. Voyager 1 swung by Jupiter at the proper angle and speed, thanks to meticulous work done by NASA's most intelligent minds at the Jet Propulsion Laboratory. Voyager 1 received the necessary acceleration as a result of Jupiter's gravity pulling on the spacecraft. But this move is a kind of art. Voyager 1 might have experienced a cosmic disaster if it had approached Jupiter at an incorrect angle or speed. The level of precision needed is astounding, but the engineers and scientists responsible for this cosmic ballet made the right decisions on several occasions. Voyager 1 and Voyager 2 underwent an amazing solar system journey thanks to these gravity aids. For example, Voyager 2 reached Uranus and Neptune with the help of gravity from Jupiter and Saturn. These dances of the stars were essential to the Grand Tour's success. Without these slingshots, the Voyager missions would not have been the same. Thanks to the accuracy of this gravity assistance, Voyager 1 and Voyager 2 were able to reach interstellar space. Gravity assists have a very simple notion, yet they are incredibly difficult to implement. The Grand Tour of Voyager 2 demanded extreme precision. Failing to make any of these slingshots may have resulted in mission failure. However, the mission team's quest for information was unwavering and unrelenting. The Deep Space Network, DSN, played a significant role in the Voyager mission's extraordinary success in addition to their skillful utilization of gravity assistance. The DSN, which enables interplanetary spacecraft missions, is made up of sizable antennas and communication facilities spread throughout the world. The DSN's job was to keep in touch with the spacecraft during the Voyager missions so that scientists could communicate with one another and exchange data and directives from billions of miles away. Voyager 1 and Voyager 2's communication and tracking systems became more and more important as they traveled further from Earth. The three locations of DSN, Australia, California, and Spain, ensured a constant connection that made it possible to gather crucial scientific data. The Voyager spacecraft was an incredible feat of engineering. Their sturdy platforms were engineered to reduce visual blur while taking photographs and data as they zipped across space. They rotated at a rate more than 15 times slower than the hour hand on a clock. These spacecraft, which were outfitted with cutting-edge equipment including magnetometers, cameras and plasma detectors, made important findings concerning the outer planets and their moons. Comparable to the interstellar phone connection that linked us to the brave Voyager probes as they ventured into the vast unknown is the Deep Space Network, DSN. But what is the DSN specifically? Its significance is equal to that of a spacecraft, despite its lack of outward appeal. Massive radio antennas, positioned strategically all across the world, especially in California, Spain, and Australia, make up the DSN. With diameters spanning from 26 to an incredible 70 meters, these massive dishes serve as cosmic megaphones, allowing us to speak with spacecraft that are located far beyond our planet. The Voyager mission's success depended heavily on the DSN. Through their cameras, sensors, and other instruments, the Voyager probes served as our eyes and ears amid the expanse of space, returning invaluable data. A dependable communication system was necessary to decipher the data they communicated and deliver fresh instructions, and the DSN was crucial in this regard. Envision Voyager 1 exploring the furthest regions of the solar system and communicating with Earth by message. This message is a feeble signal that is moving at the speed of light across space and getting weaker with time. There's barely a murmur when it gets to Earth. But this whisper is picked up by the DSN's huge antennas, which are highly calibrated to enable scientists to produce data. They boosted the feeble signal that Voyager was able to intercept. The DSN transmits commands in addition to receiving signals. Scientists and engineers are forced to make last-minute changes to plans, reroute the spacecraft, or update sensors on dynamic missions like Voyager to make sure the spaceship gets the instructions it needs. The DSN beams these commands into space. The success of the mission depends on this two-way communication between Earth and the furthest off man-made objects in space. The DSN has incredibly impressive capabilities. Its worldwide network of antennas makes it possible to communicate with spacecraft in real time wherever they may be in the sky. Highly sensitive receivers installed in the antennas enable the detection of incredibly faint signals, even ones that have traveled billions of miles. Deep space missions require this sensitivity since signal strength decreases dramatically with distance. Three primary complexes, one each in Goldstone, California, Madrid, Spain, and Canberra, Australia, comprise the DSN's infrastructure. Many substantial antennas, including some of the biggest and most potent 70-meter dishes in the world, are housed at each complex. Because of their deliberate placement about 120 degrees apart in longitude, these facilities guarantee that as the Earth spins, at least one station is in communication with a spaceship at all times. This design allows tracking and simultaneous communication with several spacecraft, as well as continuous coverage. Ensuring correct signal timing and synchronization is one of the DSN's primary duties. Due to the great distances involved, even minute timing mistakes might result in major differences in the way the data is interpreted. To ensure accurate timing, the DSN uses sophisticated atomic clocks. This allows for accurate tracking of spacecraft trajectories and accurate interpretation of scientific data. Additionally, the DSN is essential for assisting spacecraft navigation. The DSN can precisely ascertain the position and velocity of spacecraft by monitoring the Doppler shift and timing of the signals they receive. For mission planning, course adjustments, and ensuring that spacecraft arrive at their intended destinations, this information is essential. The DSN's continuous operation, which involves constantly searching for far-off signals, is one of its unique features. It maintains communication with our spacecraft, even when they are billions of kilometers distant, acting as an unwavering eye on the universe. This ongoing attention to detail ensures that we stay in communication with our far-flung explorers, enabling us to collect priceless scientific data. No matter where a spacecraft is in its orbit or route, there is always a facility to maintain contact, thanks to the DSN's global network of antennas. For deep space missions, when even a brief communication breakdown might result in the loss of vital information or the inability to send directives on time, this redundancy is essential. This meant that the Voyager missions would always be within reach while Voyager 1 and Voyager 2 investigated the outer planets and eventually traveled into interstellar space, transmitting amazing photos and groundbreaking scientific findings, like the active volcanoes on Io or the frozen shell of Europa. These discoveries might not have been made or known without the DSN. There is more to the DSN than just Voyager. It is compatible with many interplanetary missions such as those to Mars, the outer planets, and beyond our solar system. Its capacity for communication across great distances is evidence of human inventiveness and the desire to explore uncharted territory. The DSN's history is likewise one of ongoing innovation. Its capacity to manage greater volumes of data and sustain more accurate connections with spacecraft has grown along with technological advancements. This evolution pushes the bounds of what we can investigate and comprehend, ensuring that future missions will benefit from even more connectivity. Essentially, the Deep Space Network is our lifeline to space, not just an array of antennas. It guarantees that the narratives of the Voyager missions will be written, even after the spacecraft depart from Earth and enter the unexplored regions of interstellar space. We can reach farther into the wide universe thanks to the DSN, which creates a bridge between our world and the unknown. An important milestone in the Voyager probe's interstellar mission was negotiating the heliopause. This border denotes the point at which vast interstellar space begins and the influence of the Sun starts to diminish. The precise location of the heliopause had long been unknown. Early calculations suggested that it was as near as Jupiter. However, more computations improved our understanding. The heliopause was estimated by astronomer Bill Gurney to be somewhere between 116 and 177 astronomical units, AU, from the Sun in 1993. An AU is equivalent to approximately 93 million miles, which is the distance between Earth and the Sun. When Voyager 1 arrived at the heliopause around 20 years later and observed the anticipated increase in plasma density, Gurney's calculations turned out to be amazingly correct. However, Voyager 1's heliopause encounter raised interesting questions. Although the ambient magnetic field direction didn't significantly change, the spacecraft did detect an increase in plasma density. This was surprising as there should have been a discernible shift moving from an area influenced by the Sun's magnetic field to one affected by other stars. To complicate matters further, Voyager 2, which reached the heliopause at the same distance of 120 Australian dollars from Earth, also failed to detect any changes in the magnetic field. These unexpected findings challenged the theoretical models that predicted the heliosphere's nature and its interactions with the interstellar medium. The Voyager data didn't support the theory that the heliosphere would change following the Sun's 11-year cycle. When Voyager 2 reached the heliopause, the solar wind, which fluctuates in intensity with the Sun's cycle, was at its fiercest. Consequently, the expected location of the heliopause should have been farther out than 120 Australian dollars. Still, the data from the Voyagers yielded priceless insights that improved theoretical models. It is now thought by scientists that our Sun has moved from being a hot ionized zone to a partially ionized region of our galaxy. This transition was likely caused by nearby supernovae, which are old stars that exploded at the end of their lifetimes. These supernovae heated the surrounding environment and stripped electrons from neighboring atoms. The border between these regions resembles a seashore with erratic waves and inconsistent magnetic fields. Voyager's observations have shown small-scale alterations near the heliopause but minimal variations on wider scales. As Voyager 1 and Voyager 2 continue their lonesome travels through interstellar space, they leave behind the planets and moons they once called home. But what awaits these unstoppable travelers? This is a cosmic guessing game. The probes are traveling in different directions. Voyager 2 is headed toward the constellation Cetus, while Voyager 1 is speeding toward the constellation Ophiuchus. It is plausible that these spacecraft will survive for millions of years, far beyond the lifespan of our species, even if power limitations will likely force them to cease operations by 2030. They may encounter other star systems and carry with them a message from a long-lost Earth. Both Voyager spacecraft carry a golden record, a chronology of human history. It includes sounds and pictures chosen to highlight Earth's life and culture, greetings in 55 languages, music from various times and cultures, natural world noises, and pictures showing human accomplishments. Imagine an extraterrestrial race finding the golden record. This discovery might offer a glimpse into our reality, piquing their interest and wonder. Additionally, the ongoing data transfer from interstellar space by the Voyagers deepens our understanding of the universe. Scientists learn more about the environment outside our solar system from the data these probes return, even as their power diminishes. They encounter cosmic rays, magnetic fields, and plasma densities that reveal information about interstellar space's composition and the mechanisms governing our galaxy. Reflecting on the Voyager's amazing journey serves as a reminder of the unquenchable curiosity and tenacity that propels scientific inquiry. The heliopause, once a far-off and enigmatic boundary, has been crossed, raising new questions and challenges. The data collected by the Voyagers will continue to inspire and inform future generations of scientists and explorers, ensuring that the quest to understand our universe endures. Voyager 1 and Voyager 2 remain symbols of human achievement, carrying the dreams of humanity and the legacy of their creators as they journey into the unknown, forever.